Okay. So let's start today with the first part of the two sessions. One is dedicated to conducted emissions, the other to radiated emissions next week. Sorry. The other to radiated emissions next week. And we will be talking about debugging EMI and EMC problems with oscilloscopes. First, let me thank EMPS and Roden Schwartz for the invitation to make this webinar. And I hope all of you will enjoy with some experiments and some basic ideas. I will be very happy to answer any questions you have at the end of the session. Anyway, let's start considering, for the people that don't know what we are doing here in Zaragoza in Spain, our laboratory is the HFMI lab. I am working at the University of Zaragoza, and we are specialized in solving and analyzing EMI problems. Not something that is not easy, and not always we are able to solve problems. Okay, so let's talk about debugging strategy. What we will be trying to explain is that oscilloscopes are, in my opinion, one of the best instruments to make debugging of EMI problems. Basically, I find three different considerations. The first one is that the bandwidth of the oscilloscopes is easy for today to work with FFT. So they have a strong FFT that is able to go up to gigahertz. So you can use the oscilloscopes in conducted and in radiated emissions. The second important thing is that we have several channels. And because we have several channels, we are able to work with different probes. For example, we can use voltage probes, we can use current probes, we can use near-field probes, line impedance stabilization networks, and antennas. So if you are trying to measure radiated or conducted emissions, you will be using antennas or line impedance stabilization networks. If you want to do debugging in the near field, you will go to work with electric and magnetic near field probes. And if you are interested in debugging in some kind of circuit theory point of view, you will work with voltage and current probes. Today, we will be working with the oscilloscope for debugging of EMI problems in conducted emissions. So basically, we will be working with the line impedance stabilization network and the oscilloscope. Next webinar, we will cover the idea of radiated emissions, and we will use current probes and the other probes that you can see in the picture. So let's start with conducted emissions. The first important thing when trying to understand conducted emissions is that from the power supply to your device under test, you will have a black box that we call line impedance stabilization network. How is the main mission of this black box? The main mission of this black box is to offer to your product a known impedance in that direction. So the noise you are injecting in differential and in common mode is on some kind of impedance that is known for all the people. So measurements in different cities, in different laboratories are close to be similar. Not always will be similar. We have some kind of range, I don't know, plus minus 6 dBs in error, but basically we are measuring in the same conditions and we can compare with the same limits. This is the first important function of the LISN. The second important function is the idea to avoid EMI going into your setup or EMI going out from your device to the external power supply system. And finally, the third solution, the third option with a LISN is to have a voltage, the voltage that we will be measuring in the receiver. You can use EMI receivers, you can use spectrum analyzers, or you can use, like in our demos, oscilloscopes. Don't forget to use some kind of transient protector in case you are using power electronics, especially devices with strong transients, because sometimes you can destroy or you can damage the input port of your EMI receiver. And this is something that is expensive and usually create delays in the work with your design process. No? So basically, when we measure conducted emissions, we will be measuring in some frequency range, for example, from 150 kilohertz to 30 megahertz. This is a common conducted emissions measurement. Sometimes we start at 9 kilohertz. Sometimes we stop at 110 megahertz, like in automotive. And what you will see is in the horizontal axis, frequency in logarithmic scale. In the vertical axis, you will see voltage. That is because we can measure dB microvolts. This is the voltage in the output of the line impedance stabilization network. So is this voltage here is what we are measuring typically in the 50 ohms input impedance of your device, of your instrument. And you will see two different measurements, the black one and the pink one. The black one is when we are using the quasi-peak detector, and the pink one is when we are using the average detector. That is because you have two limits, the quasi-peak limit and the average limit, the two lines that you can see in the picture. So when we measure our device, we will see different energy at different frequencies. Sometimes this energy is easy to identify. In this example, I start here at 500 kilohertz, and going from one peak to the other peak, we find that the distance is 500 kilohertz. That means what? Is that they are harmonics of some specific circuit that is switching in a fixed frequency. No? Sometimes in the emission, you will see a broadband emission, something like this, okay? Something like this, that looks like a mountain, no? This is typically coming from resonances. One of the examples of resonance is usually ringing because of the parasitic inductance and capacitance in the layout and the packages of your components. And something that is very important is to be able to reduce these emissions over the limits going down in this way. So instead of being below the limits in this way, we will try to go below the limits in this way. That is because if you are below the limits, I mean, you are complying, but your emissions are increasing when you go to the 30 megahertz or the 100 megahertz frequency, you are complying with conducted emissions, but you have more probabilities to fail later in radiated emissions that start at 30 megahertz. If you pass conducted emissions going down, when you approach to 30 megahertz, you have more probabilities to not having problems in radiated emissions. Anyway, our problem will be to reduce the peaks below the limits. My main recommendation is if you are in this situation, you cannot consider here that you are complying. If you are 0.5, 1 dB below the limit, forget about the idea of you are complying. Because if you change of that laboratory, or if you measure different units of your product, you will see some kind of changes. No? So my recommendation is to try to reduce the limit at least 6 dBs below the limit. And usually we will try to do this redesigning the circuit with the components, the layout, or applying a spread spectrum like Florian was explaining in the first speak, or we will try to solve this problem traditionally by filtering. Filters are expensive, are big, and the most strategical work is to try to minimize the size and the order of this filter. So what we will be doing today is to replicate a very simple measurement with a small device under test. I will be using a small buck converter, and we will try to replicate something similar to what we find in a CSPR25 setup. It's not perfect, you will see now in the camera, but we will be able to explain the main ideas about using the oscilloscope for this task. So from a power supply that is external to my setup, I will get something like plus 20 volts, 15 volts, 16 volts, something like that. And in the output of my device, I will have 12 volts to power, sorry, this is 20 volts. And my buck converter is powering a fan that is working at 12 volts. In this way, I take some kind of current from the buck converter. Look at the setup. The setup explained that you need a ground plane and some kind of isolation material between the device and the test and this metal plane. And we will be using 2 LISNs. The use of 1 or 2 LISNs depends, following the CSPR25, with the length of the cables. You have more than 20 meters in cables, you need 2 LISNs. You have less than 20 meters, you can use 1 LISN. But you will learn today why we are using 2 LISNs. Basically, the idea is that we will be able to separate common mode and differential mode, and this is very important for designing our filter. You can identify additionally in the picture that they have 2 capacitors, 1 microfarad external to the LISN. This is because if we put the capacitors inside of the LISN, we will not be able to use the LISN for immunity, okay? So in my setup, the 1 microfarad capacitor is outside of the LISN, and in some commercial LISNs, you can find the capacitor inside of the LISN, but you can switch on or off internally. So from each LISN, we will have a BNC connector that is basically here and here, and sorry, here and here. And then with two uniform transmission lines, two coax cables, 50 ohms coax cables, you can go to the EMI receiver, to the oscilloscope, or you can terminate with some kind of 50 ohms termination. Look at this. The positive terminal of the power supply goes to the one of the LISNs to power the positive terminal of the device under test, and the negative terminal of the power supply goes through the other LISN to power the negative terminal of the device under test. The negative terminal of the LISNs is connected directly to the ground plane. So when we are measuring with LISN number 1, we are measuring the noise in the positive line. When we are measuring with LISN number 2, we are measuring the noise in the ground line of my device under test, okay? So the metal plate is some kind of reference structure, okay? If you are interested in different regulations, this setup can change. For example, in CSPR 16 or any other similar regulation, you will need to put your device on top of a table that is non-metallic, and the ground plane is in the floor and in the walls. But obviously, you need to check the correct setup for your application. So now that we have this fast description of the setup, let me show you how we will be working today. Basically, we will have 4 different cameras or screens. We have the screen, so we will be able to draw in the tablet. We have the screen of the oscilloscope. The screen of my oscilloscope is an RT06 from Rod & Schwartz. Let me make a preset. So we see in yellow color is the voltage in channel number 1. This is time domain. In the bottom left, you can see a picture of my setup. Now I will describe soon. And here we will see in the bottom right, we will see details of the device under test. So now let's explain basically how is the setup for our experiment. This is the setup, okay? So you can see here, let me show you. This is the input voltage. Here you have here between 15 and 20, 30 volts, no? This is a filter. This is a filter that is used to be sure that no noise is coming from the power supply. This is especially important if you are using a switching mode power supply in your laboratory. So the power we apply in our setup is clean as possible. The negative terminals of the LISNs are connected directly with 2 short and wide connectors to the ground plane. The ground plane is represented with this aluminum foil. So here, between the red and the red terminals of the line impedance stabilization networks, we have here a voltage that is the 20 volts going through this low pass filter to the output to power my device. You see the output of LISN number 2, the output of LISN number 1 to go to the oscilloscope. You want to see how is the setup, we can switch to the, let me show you here. Let me change the angle of the camera, and you will see that close to the line impedance stabilization network, we have the oscilloscope. Here is the oscilloscope, and I will be connecting the output of the LISNs to channel number 1 or channel number 2. Oh, sorry, I didn't change the camera. You can see here, okay? So you see here the oscilloscope, channel number 1 and channel number 2 will be used to measure the output of the LISNs directly, okay? So let's connect again here to see the details of the device under test. Okay. So if we are interested in measuring conducted emissions of the device, we will need to put our device on top of the
dielectric material. The height of the dielectric material is usually explained in the regulations. We need to power our device. So I will be using this short cable, in this case for my demo, and we will be powering the power supply here. So now you will see that if I switch on the power supply, the green LED is on. Let me see, you can see here the green LED, okay? And now we can connect the fan, that is a 12 volts fan, okay? I'm not sure if you see in the camera that the fan is rotating, no? So it's working as expected. So let's connect here the setup. So we are ready for measuring. Obviously, if your product is inside of a plastic or a metallic enclosure, you need to replicate the full structure to make the measurements. But because I want you to see the internal hardware, I am not using the case of the product, okay? So now that we are here, we can explain what happened in the line impedance stabilization network. Look at this. This is the input voltage. So really, in my slide, I am talking about mains, line, neutral, and earth, but forget about this. We are in DC. This is the positive, this is the negative, and this is the metal plate, the chassis, no? So you can see that for the positive, I have one circuit that is something like an LC circuit. This is the blue line, the blue circuit, okay? Something like this. Usually the resistor that you see here, the 1K resistor here, in mains applications is used for safety. So the capacitors are discharged in this specific application, or can be used for damping resonances in the LC circuit. In my setup for CSPR25, instead of 50 microhenries, we have 5 microhenries here, because the inductance in the automotive lines is lower than the inductance that is expected in the mains application. And you can see that we have another LISN. They can be in the same box or they can be in separated boxes with an exact and equal circuit. Okay, this is 1K. So where you find the output of your circuit? The output of your circuit, of your LISNs, is here and here. So you can see that goes to one connector and you go to the other connector. This is out number 1, and this is out number 2. This is the idea. So these connectors are these connectors in my setup. 1 and 2. 1 and 2. They go to the oscilloscope or to the EMI receiver. Okay, so what happened inside of the LISN? Inside of the LISN, you are receiving differential mode noise in this direction. So the differential mode noise, when arriving to this point, take the decision to go through the capacitor that is a lower impedance than the 5 microhenries inductor, goes through the capacitor that is close to a short circuit and goes to your 50 ohms resistor. So here we have the 50 ohms resistor of your receiver. So you can see that the voltage you are measuring in the connector 1 is 50 times the differential mode voltage. But this connector, this ground is connected here, is connected here, is returning in this direction, is returning in this direction, and this is the return path for the differential mode. So how is the impedance that the device under test see in differential mode? Is going in this direction, 50 ohms in series with 50 ohms. So the impedance you see in differential mode from the device under test is close to 100 ohms. This is important when you are designing the EMC filter. And what happened with the common mode? With the common mode, the current is going, let me take another color, for example, pink. The common mode is going out here and is going out here. And you can work in the same way. The current of the common mode goes in this direction, goes in this direction and goes in this direction, and it's going in this direction. So something that is very important is that the voltage you get in connector 2 or the voltage you get in connector 1 is neither the differential mode or the common mode. This is a mix of differential mode and common mode. And this is an information that is very important if you are interested in designing the filter. So what now we are going to do is to measure with my oscilloscope how is the noise we are injecting in the setup, in my setup, when the power supply is on. So let's switch to the screen of the instrument. You see here is an oscilloscope. This is voltage, this is time, and in yellow color, this is the output from the signal in channel number 1. If we switch here, channel number 1 will be used to measuring LISN 1 here. And the second port is terminated with 50 ohms. If you want to measure in LISN number 2, the negative terminal, you need to change one by the other, okay? You can see in the screen of the oscilloscope that we have the time domain signal of the emissions, okay? Anyway, I am not going to use the oscilloscope with this software. I am going to open another software that is this one. This is a software that is coming with the RDO6, where I can specify what frequency range I am interested in. For example, with V, I am interested between 150 kilohertz and 30 megahertz. I can specify, for example, the peak. I'm going to consider that I am interested in this limit and this limit for the average, and we establish the setup. Now we need to put here 0 dBs, and we set up the RTO, something like this. Now we recover the FFT traces from the oscilloscope. And in a few moments, I will show you, it's here, sorry, here, yeah. Okay, so you can see here the peak and the average emissions of my device. If we go to the screen of the oscilloscope, you can see this. So the original channel number 1 in yellow color and only time domain. Now we have two screens. One is the quasi-peak measurement. The other is the average measurement. And with the software, we have used the mask option of the oscilloscope to create the limits. So we can identify if we pass or if we fail in our emissions. So with this product, actually, I am failing in conducted emissions. I am some dBs over the limits in some kind of narrowband emissions that looks like they are very periodic from peak to peak, okay? Something interesting. We need to consider if the LISN don't have this accessory. Let me go here. We need to consider to introduce some kind of protection for your EMI receiver. What I am going to introduce here is a transient protector. The transient protector usually is some kind of attenuator with some kind of diodes that clamp any kind of transient that can damage your device. So if we repeat the measurement, let's go to the previous software. Look at this. The first peak is 70 dB microvolts. Now, if I repeat the measurement while I am introducing the transient protector, the 70 is going to 60. Why is this? Because if you go to the setup, the signal that is going out of the LISN, when passing through the transient limiter, including attenuator, is introducing here a 10 dBs attenuation for the signals. So you need to know how is the frequency response of this accessory. If you introduce one amplifier, or if you introduce a long cable, something like that, you need to know how is the frequency response of this accessory, so you can correct in the measurements. So if I go to the software again, here you can see transducer factors. If I put here 10 dBs, that is the is basically constant in all this frequency range, and I configure the oscilloscope, when I recover the traces, you see that the 60 is going to 70. That is the correct measurements. Be careful about that. And something that is important with oscilloscope is to use the input coupling with 50 ohms. Because look at this. The peaks are going down, going down, going down. But if by error, I configure the oscilloscope with 1 megohm, let's go to 1 megohm, that is typical in many oscilloscopes that they are not very high in bandwidth. The idea is that configuring the oscilloscope and recovering the measurements, you will see, let's wait a moment, let's recover. You will see that I have the peaks going down. Up is not very important here. Oh, let me do something. If not, I will repeat later. It's because I have the attenuator. Let me remove the attenuator. The attenuator is removing the reflections. So let's go here and let me repeat. Now I am going to put here again 0 dBs in the transducer factor because I have removed the attenuator. And let me put 1 megohm, set up RTO. And now let me measure again. Let me measure again. Let me see if it works. Okay, you can see that the peaks are going down, but I have here some kind of a mountain increasing the amplitude. If I increase the length of the cable, if this cable instead of 20 centimeters is, for example, 1 meter or 2 meters, this effect, this mountain effect, increase a lot. And this is because we are creating reflected signals in the transmission line. So remember, 50 ohms in the input impedance of the oscilloscope, and introduce here the transducer factor of the transient limiter or any other element you can be interested in introducing in the middle of the signal. So now I am not going to use the transient limiter in my experiment. So I set up the RTO with this configuration, and because now is 50 ohms, the input impedance, the reflections must be removed. So let's go here to introduce FFT. Okay, so you see the reflections here are reduced. This is very important. If not, you will start to see peaks that are not from your device, are peaks created by your setup. Well, so what can you do to reduce these emissions? What you can do basically is to review the design and to try to minimize these emissions. The good strategy is not to introduce a filter. The best strategy is to try to switch slower, considering efficiency, perhaps to introduce a spread spectrum if possible. Perhaps you can change the layout. Perhaps you can put the aggressive elements far from the input connector of the cables. There is a lot of things to do before considering filtering. But at the end, in many, many products, you will need to introduce some kind of filter. And the important idea is that the filter be as small and as cheap as possible. No? So let's try to see what happens if I introduce a filter. So now we return to my setup. And what I am going to do is to introduce this filter. Let me show you with the camera. Let's switch to the detail camera, only device, here, transition. Okay, and here is my filter. Obviously, there is no time to explain the design of the filter. It's only for basic demonstration. I have 2 capacitors. I have 1 common mode choke and 2 Y capacitors. I know that in this application, we don't say usually X and Y capacitors because there is no safety rules like with the mains, but in this way, all the people is understanding. These X capacitors from positive to negative, and Y capacitors that go from positive to chassis and from negative to chassis. Additionally, I have a common mode choke, but this common mode choke is being short-circuited. So you can see here that with these jumpers, I am short-circuiting the common mode choke. So now the common mode choke is not activated and the Y capacitors will not be working because I am not going to connect the Y capacitors to the metal plate. So if we introduce the filter in place, let me disconnect Let me connect here. This way. And now we power again. Okay, we put here the setup. Let me change here. You can see that this is my filter, okay? And theoretically, I have now only X capacitors in parallel. So it's a filter with an order equal to 1, okay? So we go here to the measurements. Let me go to the software of Roda and Schwartz. So this is our actual measurement. Let me take a picture of this result. This is before the filter, and then we will be able to compare. And now let's recover again the measurements. So let's take here FFT. Okay. Okay. So you can see that I am removing a lot of emissions, but in some emissions I am failing. Instead of working with the filter in some kind of trial and error, the recommendation is to work with trying to identify what is common mode and what is differential mode. You have the possibility to use an external device that is called LISN mate, or is working with transformer, resistors. There is different methods to do that. But what I like to do many times is to work with the oscilloscope. So let me show you how is the setup of my instrument here. And what I'm going to do is to work with this output going to channel number 1. And now I remove the 50 ohms termination and I connect this to the channel number 2. Let me preset the oscilloscope. And then when I preset the oscilloscope, look at this. Is channel listen number 1 goes to channel number 1. Listen number 2 goes to channel number 2. And then what we see is this. Let me see. What we see is this. This one, okay? So let's activate channel number 2. Let's review that in channel number 2, we have 50 ohms. And let me check that in channel number 3, in channel number 1, we have 50 ohms. It's very important to have 50 ohms in both channels. Okay, something like this. Channel number 2. Let's see, channel number 1. This is a emission in channel number 1 and in channel number 2. Now, when you have the output of the two listens, listen 1 and listen 2, if you add the two outputs, you will get 2 times the common mode emissions. If you subtract L1 minus L2, you will obtain the differential mode emission multiplied by 2, or 6 dBs more. So what I am going to do is to go in the oscilloscope, and I'm going to create a new function. It's in the math function. Let me go to here, to the math function. I'm going to work with the equation option, and then you can go here and to introduce channel number 1. Let me remove all. Oh, let me try to do this here. Here. Channel 1 plus channel 2 divided by 2. Okay. Why dividing by 2? Is because I am trying to calculate the common mode. Remember, addition means common mode. Subtraction means differential mode. So when we go here and we apply enter, we have math number 1 here. Let me remove the time domain signals. And now math number 1 is this. Let me increase the intensity of the signal. Okay, something like this. And now we apply the FFT. We go here and we say from 150 kilohertz to 30 megahertz, we can introduce a resolution bandwidth of 9 kilohertz. and we apply this to math number 1. And now in math number 2, that is the FFT of this calculation, we can go to a scale, horizontal scale, and we can put this in horizontal scale in logarithmic way, okay? Something like this. So what you can see is that in my measurements, this is the contribution of the my emissions in the common mode. If we are interested in the differential mode, look at this. We can compare this. For example, let me save in reference. In reference 1, I'm going to save math number 2, update. Okay, so this is the common mode. Okay. Sorry. I'm going to repeat because I am measuring. Let me show you. Transition. I am measuring with a filter. I need to make this measurement without a filter. Okay. So now it's easy to solve the problem. So we are here again, and we update. This is the common mode. So let's update the reference. Update. Okay. So this is the common mode, the left side, and now opening the math, we can change the equation. Oh, sorry, not this one. We can change the equation to calculate the subtraction. Okay, instead of this, instead of adding the 2 channels, let me back and minus. With the minus, I will be calculating the differential mode. And now it's okay, this one. Okay. So you can see at what frequencies the dominant effect is differential mode, and at what frequencies the dominant effect is common mode. And this is very important because then you can separate in a separated way to design the common mode filter, common mode chokes, Y capacitors, and the differential mode filter, X capacitors and differential mode chokes. Sometimes common mode is not important, and the dominant effect is the differential mode and the opposite. When you have this work done, then you can go again to your software, and then you can introduce the full filter, okay? What I am going to do now is to connect the filter that in theory was designed considering these ideas. Let me show you the camera so you can see what I am doing, no? Now the filter is in place. We go here, we see the setup, and we measure with the filter in place. And we will see that we are not complying. Let me show you. What happened? Wait a moment. It's not working. Oops. I am closing the software. Sorry, let me open again. Here. Sorry, it's because I have been working in parallel here about both here, and then let me put the key, the quasi-peak limit, the average limit. Then we set up here 0 dBs set, and then we repeat again, set up to RTO, and we measure. Now is the emissions with the filter in place. And you can see that I will not be complying. Oh, sorry, it's failing. I don't know why. Oh, sorry. I forgot to make the B measurements. This one, quasi-peak, sorry. I am trying to arrive on time. This one. I'm doing the setup. Let me introduce here 0 dBs in the transducer factor because I am not introducing the transient limiter, and let me recover the FFT traces. Okay, and you can see that I am not complying, fully complying. And sometimes this is due to things like this. Let's go to the cameras and let's see what happened. No? Now, the connection of the Y capacitor is not done to the metal chassis. No? So I have this long wire. This is not a good strategy because this is inductive, but for the demo will be working. What you are going to see is how I connect directly with my finger to the chassis, the Y capacitors. No? So if we go to the software, let's go here, and let me activate the continuous update. Now the software is updating every second, okay? So now the Y capacitors are not connected this way. Now I'm going to connect in this way. Chip, chip, okay? So let's go here. And you can see here, this is not connected Y capacitors connected. Oops, sorry, something is wrong here. Uh-oh, effecto demo. Why is not filtering? I don't know why it's not filtering now. Sorry. Well, anyway, I don't know why it's not filtering, because in theory, something I am doing wrong. Okay. It's because I discovered what happened here. The idea is that I forgot to enable the common mode choke. Remember, the common mode choke is disabled with these jumpers. So now I am going to remove the jumpers. So we can check here how is the result. You can see here that now I am better. In some peaks, I am touching the limit. I am not 6 dBs below the limits. And now is when I am going to touch with the wire in the chassis. Okay, so this is the emission here. This is what I am doing. Remember, in my previous measurement, I forgot to remove the jumpers that were short-circuiting the common mode choke, and that is because it was not failing for the common mode. No? So now we go here. This is without the capacitors touching the metal plate. Now I am going to touch. Okay, so you can see now. Okay, so I am really below the limit. And it's a very useful technique to identify if you need to change or to add components in common mode or in differential mode to check if something is well connected or not bad connected. Well, this is basically the idea of how to work with the oscilloscope. And now let me show you something that is interesting, that is a good design. This is a technique that I like to show you from MPS. I will be working with this evaluation board. No? This is an evaluation board for a step-down converter where they are applying some interesting techniques to minimize the emissions. That when you minimize the emissions at the design stage, you will have the possibility to reduce the size of the filters and you have a quiet element. No? The previous DC-DC converter was created with bad techniques, considering the size of the switching node, the distance between the components, the ringings, etc. No? In this case, we have a 4 layers PCB, and I will comment later some specific ideas that are useful for this PC board. If we go to the setup or to the device window, now you will see that my PC board, let me here, my PC board is now this one. Oh, sorry. This one. Let me use a short cable to connect the power supply. I will use the same power supply like previously. This one and this one. Okay, I am introducing close to 20 volts. And in the output, I will be using a resistor, a power resistor. So I am able to put different load conditions to the converter. Okay. So let me show you the resistor. It's here, and here you have the converter. And the converter now is working at full range, and we are going to measure the emissions. Okay. So you can see now in my software, this is the emissions of the product. Okay, you can see here. Look at the emissions. It's close to the 0 level. Let me switch off the power supply. When I switch off the power supply, you will see the emissions from my product. It's something like this. This is with the power supply off. This is with the power supply on. Okay. So I would like to explain, I am interested in these suggestions because for all of you interested in designing low impedance, low emission circuits, it's very important to understand some of these techniques. This is for a buck converter, but you can understand this for any switching topology. What is the most important or the two most important elements in a switching device? In a switching circuit, in a switching device, the most important things are the switching node. Remember, is where you are creating harmonics and usually ringings. This is a high DVDT node. It's a strong electric field area and is connected to the inductor. So you can see here that if I take a look at this inductor, if you use a small inductor, this is much better than using a big inductor. If you use a big inductor, that means it's more metallic structure where you are applying this high DVDT, and you have more probabilities to extend the noise to nearby areas. Obviously, if the DC-DC converter is close to cables and connectors, this is the worst situation. And the second part that is very important is this one. If you consider here that this is the voltage, input voltage, and we try to draw a simplistic idea of the DC-DC converter, something like this, the switching node is here, and this is the ground. Let me draw in this situation. So you can see here, these capacitors that are represented with this. So what happened with these capacitors? These capacitors have the function to give to the device all the transients we need to work as expected. And this loop is really critical. This loop must be very, very, very small. And this is what you can find in this design. Look at this. You have these ideas in your slides, but let me show you the top area of the PCB. In the top area of the PCB, you will find that the decoupling capacitors, the 4 decoupling capacitors, let me draw here. Let me reduce the size of the X. You will find 2 big capacitors, this one and this one, and later 2 smaller capacitors to work at higher frequencies, this one and this one. And you can see that one symmetrically in this position to the input voltage. The node for the input voltage is this one. Okay, this is the node for the input voltage. No? And you can see that one capacitor is connected here to ground, and the other capacitor is connected here to ground. Why is this? This is because if you put the capacitors in this position, you put the capacitors symmetrically, and the ends of the capacitors are connected to ground, and this is the V in voltage. The idea is that the current that you are injecting in the device that is switching has opposite directions, and the magnetic field is canceled. If you repeat this idea in the input for the 4 capacitors and in the output for the capacitors in the output circuit, you will have exactly the same idea. This is one of the most important things. Another important thing is that in this setup, the filter is close to the connector, to the input connector. This is the input connector, but is in the bottom layer. If you put in the bottom layer, you will reduce a lot the possibilities of L1 and L2 of picking up noise. L1 and L2 are here. L1 and L2 are here. This is a filter, the filter we are using for our device. It's L1 and L2. No? So it's a second order filter if we plot from the device under test. No? This is the device under test. This is the LISN. No? If you use a 4th order filter, you will get several advantages. The first one is that you will get, for each component, you have 20 dB per decade of attenuation. But additionally, the inductors will be smaller in size. That means that they are less they have less possibilities to pick up noise from the environment. And additionally, the size of the filter will be reduced and the filter is more effective. And additionally, look at this, the filter is in the bottom layer and the distance between the first stage and the second stage is some millimeters. They are not close one to the other because in this way we avoid the possibility of the two inductors are coupled. Believe me that in high frequency, this coupling is extremely critical. And look at the capacitors. The capacitors additionally are symmetrical. If you are interested in this kind of ideas, because we don't have time today for working in detail with this design, I recommend you to check the application note and the documents you can find in the slide from MPS. MPS has a strong experience in EMI and EMC. They have a very impressive EMC laboratory in Germany, and I had the opportunity to be there in two times. And really, these kind of techniques can save a lot of money and a lot of problems in the future if you learn to apply them. The only question I need to explain is that they are using a ground plane with a slot. You can see here this slot. So they have something like they can call dirty ground, and we can have some kind of clean ground. So my recommendation for you is if you don't understand really what you are doing separating grounds, don't do that, okay? So really with this separation, they get something that is very, very, very clean. But believe me, if you don't know how to do that, don't separate grounds. But the other techniques are really important. The size of the components, the disposition in symmetry, etc. No? So I hope you enjoyed the webinar. 55 minutes pass so fast that is very, very difficult to comply with the time, but thank you. And I will be happy to answer any questions you have.
All right. Thank you, Arturo. Really good demonstrations there. Just a reminder to everyone that we have our next session on the 14th, so same times as today. So I think most people registered for both, but if you haven't, go to the monolithicpower.com website and register again. Arturo, we do have a bunch of questions in already, so I don't know how you're doing for time, but we can just start jumping in.
Let's go.
So the first one is one UF and AC film cap.
Yes, you can have one microfarad AC film cap, yes.
Okay. This is from early too. This is for DC. What about AC? The AC voltage is already reduced to applied to the measurement device.
I am not sure I understand the question. For AC, it's exactly the same idea. The LISN is a low pass filter, so you can pass DC or you can pass 50, 60 hertz, and the circuit is exactly the same. It's basically it's an CLC filter. So I am not really sure I understand the question, but it's basically the same idea.
Okay, thank you. Next one up was, is it not necessary in some way to take into account the frequency response?
Yes, you are right. In the transducer factors, you need to introduce the LISN factor, as I was explaining, to introduce the transient protector factor. The idea is that with this LISN, I have around 1 to 3 dBs in all the frequency range up to 300 megahertz. So I was not considering this was important. But you are right. You need to consider how is the frequency response. And usually the manufacturer, you check the LISNs from Rodenswar, they will give you a detailed frequency response, and you can introduce this in your measurement device.
Thank you. Then they just want to know what oscilloscope and bandwidth do you use?
Well, my oscilloscope is now RTO6. The bandwidth is 2 gigahertz, but you have seen that for this application, you don't need to go to gigahertz, no? You can go up to 500 megahertz, something like that. So consider how is the bandwidth you need. But if obviously you will be interested in radiated emissions, probably to have 1 gigahertz or up to 6 gigahertz could be interesting.
Thank you. Is it a good recommendation to use short cables from LISN to EMI receiver?
Yes, it's it's a very good recommendation. Remember that the length of these cables must be as short as possible. Obviously, you can use long cables, no? But in theory, because cables are not ideal. If you use more long cables, probably you can have the possibility to introduce more artifacts. What I recommend is additionally to have short cable as much as possible. Perhaps you cannot work with this length. You will need longer cables. But what is important is that the two cables must be exactly equal. Same manufacturer, from the same time of manufacturing. So you are sure that the cables are symmetrical, the same characteristics, and especially if you are interested in adding and subtracting to calculate differential mode and common mode, because they need to have the same delay and the same attenuation in the two paths.
And the next one was just about the name of the application software that you were using to draw the peak and quasi-peak limits on the oscilloscope screen.
Yes, the application is called let me see how is exactly the name. The name is RTX Precompliance. It's a software that comes with the Roda and Schwarz oscilloscopes. Let me show you here. This one is EMI Precompliance tool for Roda and Schwarz oscilloscopes. See, you call to your distributor of the oscilloscope for Roda and Schwarz, probably will inform you.
All right, and it looks like the next one was the same question. So we've already addressed that one. This one is asking, will a snubber help here? But I'm not sure. This was about a half an hour ago. I'm not sure where in the presentation that one got asked.
Well, the snubber here will not help, in my opinion, no? A snubber probably is a good option when you have something that does some kind of ringing. And if you introduce some snubber, you can reduce the ringing. But usually the harmonics you are experimenting in some specific frequency range are related with the square wave signal in the switching node voltage. No, the ringing usually, instead of this envelope, will create this mountain. And this mountain is what you probably will be able to solve with the snubbers, but not the amplitude of the harmonics. The amplitude of the harmonics must be reduced in other ways, reducing the switching times or increasing the switching time, or with with spread spectrum, blah, blah, blah.
Great. And then I think you had, what kind of filter is preferred? You had introduced a filter in.
Usually when I am working with companies, the filter they use is the filter that was working in the previous unit or the previous product. No? But in my opinion, the first thing to do is to separate common mode and differential mode. And then you try to solve the problems separately and then to combine. No? So in this way, you will be able to design some kind of optimized filter. No? It's not an easy topic, but it's very interesting, because usually the filter in power electronics today for for automotive can represent 30–40% of the size of the PC board. No, so to minimize the size of the filter can be very, very important.
Yep. Next up, can you emphasize on the quasi-peak and average measurements? Difference between the two and any best practice considerations we should follow?
Well, with quasi-peak, you have three basic detectors: the peak detector, the quasi-peak detector, and the average measurements. The peak detector is looking for the peak of the signal, of the peak of the EMI you are injecting. The average detector is identifying how is the average of this signal. And the quasi-peak is some kind of detection of how repetitive is the peak. So you can have a peak that is in some value, but it's not repetitive or is happening every a long time, no? So a quasi-peak usually is a measurement that take more time. So for debugging, my recommendation is to use the peak detection. And if you pass in peak, you will pass in quasi-peak. That is the idea. And the peak detection is additionally faster. So that is basically the idea. You have a lot of books, application notes, and references where you can learn the schematics and the waveforms that you can obtain from these three different detectors.
Okay. Any different on LISN configuration topology are required in case of DC-DC or AC-DC power supply implications for or applications for EMI measurement?
Well, if you consider that the the most basic circuit for the LISN is something like this, is one inductor with a capacitor here, another capacitor here, and here you put the 50 ohms impedance of your oscilloscope, something like this. This is, for example, line, neutral, positive, or negative in your line, and this is the chassis, the metal plate. In AC or in DC, this inductor is typically 5 microhenries. In AC, this inductor is 50 microhenries. And for DC, these capacitors are in hundreds of nanofarads. And for AC, these capacitors are in microfarads. So basically what you are trying is to represent the impedance that was agreed for the different applications. The impedance is different in the inductance value because of the typical length of cables, no? And this is something that is trying to represent the real world, but obviously is not able to match any circumstance. Something that is important in the AC situation is that if you don't have a specific ground system for your LISN, you will need a isolation transformer, because these microfarad capacitors will be connected from line to earth and from neutral to earth. So you will have a lot of leakage current, and you will fire the protection system of your installation. No? Manufacturers solve this circuit in different ways, with very simple circuit like this one, or with several stages of different inductors and capacitors in parallel, but with the same idea, to offer a known impedance. Additionally, many of them introduce some kind of transient protector, so they are able to protect your system from transients while you are working, especially in power electronics or high inductive loads.
Great. Next up, C4 and R5 appear to be snubber circuits. Do I need to place this on the same side as the IC?
Okay, I suppose they are referring to this one, this area here. Okay, R5 and C4. You can work with them for the EMI, but be careful. Be careful because the efficiency of the converter will be very related with the values of these components. Anyway, as you say, these components must be exactly in the same layer of the components of the IC. So usually all the components connected to the switching node are not recommended to go through the layers, because going through the layers can corrupt other traces or other areas that are going close to the vias. No, so yes, put the components in the same place, in the same layer of the IC.
Okay, and then why did you say the inductors were placed at the bottom? And this was kind of in the same place in the presentation.
Yes, this is not mandatory. I have solved problems where the filter is in the same position, but consider, for example, that this is the filter. This is the filter we are designing, okay? And this is my DC-DC. So what happened in the DC-DC? In the DC-DC, you have additional inductors and you have loops created by the different components. So what happened if they are connected close one to the other? If you put the filter very close to the DC-DC converter, you can have signals being coupled to the inductor, especially if the inductors are big. No, so if we put in the different layers, that means that between them you will have a ground layer that is sealed in. It's something like they are like when you are doing the layout of a PCB and you want to avoid crosstalk between traces. No, you have an aggressive signal and a sensitive signal. One of the strategies is to route the aggressive signal in the layer number 1 and the sensitive signal in layer number 4, for example. No, in this way, you have less crosstalk, less coupling. So this is the same idea. Other possibility could be shielding. No, you could shield the DC-DC converter to minimize the possibility to inject noise in the filter. Because if you inject noise in the inductors of the filter, this noise go out, bridging the filter.
Great, thank you. Outstanding presentation. I've just been dismissing these ones, Arturo, but lots of compliments in here too.
Thank you.
Then what is the name of the evaluation board you were showing?
Okay, you have in the slides is this one, EVQ 4431. Is that evaluation? Yep.
We'll send out the presentation by the end of the week to everyone too, so you'll be able to see that and just find it on our website.
Yeah.
Can you briefly explain the difference between the dirty ground and the clean ground, or where to find info about it?
Well, this is a topic that can we need to talk about this a lot of time, no? But basically consider that this is the IC in the top layer, and you have some trace that is the switching node, and you have some traces that are considering the ground for the power, no? And you have another trace that is for the input voltage, no? So this is connected in layer number 1. So if you have loops, you are creating loops in the first layer. I mean, there is the return path for the high activity currents is not in the second layer. It's in the same layer where you have the switching layers, okay? And then in the lower layer, in the layer number 2, you have a ground. So how is the idea? The idea is that this dirty ground, let's write here dirty. This dirty ground is only in top layer, is working in some kind of area, in this area, and is connected to the second ground in the top layer in some specific vias, but not with multiple vias in any position. If you analyze the data sheet, you will see what I am trying to say, okay? You can see here, this is the dirty ground. I am not able to see here clearly. My recommendation is to check to the data sheet. So one of the ideas to do this is basically that if in the top layer, you have a current, aggressive current that is taking this loop in some way, you put in the lower layer a plane, you will create inducted currents in the second layer with a current that is opposite. That means what? The magnetic field at some specific point created by one of the currents is opposite to the other one. It's like the same idea. You have a loop where you have current, and you put below this loop, you put a metal plate, the emissions at some specific points are eliminated because the currents inducted in this plane cancel the magnetic field created by the first. So this is basically the idea, okay? The idea is to be able to have the high currents circulating in the dirty ground in the top layer. Right? Anyway, if you are not able to understand this concept, don't do that, and put the ground plane below the components of the IC and all the switching nodes, and as close as possible. Okay. So in this way, multi-layer boards where the second layer is close to the first layer are better than 2-layer board where the distance between the first and the second layer is 1.6 millimeters or something like that. As close as possible is a good technique, and you will have a quiet system. No?
Okay. How critical is it for the filter damping factor from your experience? Oh, how critical is the filter damping factor from your experience? I guess that is the question.
Yeah, the idea is this. If you put a filter and it's a low pass filter for EMC in common mode or in differential mode, probably you are thinking in this. But related with the terminal impedances and the parasitics in the components, perhaps you have this. And what happened with this? This is 0 dBs. This is, I don't know, 5 dBs. That means that at this frequency, the voltage in the output will be higher than the input voltage. So for example, if you have a system with a switch, when you have here, I don't know, let's say 12 volts, when you switch on, the voltage at the input of your system try to go from 0 to 12 volts suddenly, okay? This is a step function. If you pass this step function, goes through this underdamped response, the output will go to this behavior, okay? Something like this. Sorry, something like this. So this is 12 volts, but this can be related with Q times the input voltage. So you have a Q of 10, that means you can have 10 times the input voltage. So this is in my experience, no? Because there are other probability to create problems. But in my experience, where I have seen this more important, it's in immunity test. When you apply immunity test, this underdamped situation can create in the output of the filter transients very high, including in the situation when you have here a varistor. You have here a varistor, and perhaps the varistor is clamping the input voltage, but because of this underdamped situation, you can recover the voltage in the output of the filter.
Great, thank you. Could we do the same DM and CM separation with 2 RF voltage probes instead of 2 LISNs, larger equipment?
No, because you need to offer to the product some specific impedance, and this is what we get with the line impedance stabilization networks. So I think the answer is no. No, I think.
Okay. Let's see. The output capacitors from the MPS evaluation board are placed parallel, not 180 degrees as the inputs are. Is this all right for the emissions, or is it best to place them also at 180 degrees?
Okay. It's different because here, let me see if I understand the question. Let me see, where is the slide? This here. Okay. The idea is that for the input capacitors, the ground terminal is here. This is the ground terminal, and this is Vin. Okay. But for the output capacitors, this is the inductance, and the 2 capacitors are located here. One of the things that you get with this situation is that the current that is trying to go out from your system and is able to pass through the inductor is returned in different phases to the through the capacitors. So this is the correct orientation. And additionally, the idea is that this capacitor and this capacitor close to the inductor creates some kind of shielding of the inductor. So the 2 capacitors close to the inductors create this shielding. So anyway, if you put the inductor in this position, let me think, and you put the capacitors in this orientation, you will get some cancellation in the same way. So it's correct, but you will not get the shielding effect of the capacitors with the inductor. So both situations can be good. I prefer the one you have in the MPS board, but the other placement is correct too.
Okay. Can I use one LISN box and do one conductor measurement at a time?
Yes, you can. This is what you get when you buy a LISN with a switch. It's a switch in the front panel. So you switch from line to measure line, or to measure neutral, or to measure positive and to measure negative. The only disadvantage is that you will not be able to calculate differential mode and common mode. This is the only difference, because they will not be synchronized, and depending on your instrument, perhaps you only have the spectrum and not the phase. So you will not be able to add or subtract.
As you talked about the coupling between the two magnetic components, is it a big problem when I put the input filter and the output filter close to each other?
Yes, yes, it's very, very important. Very, very important. Typically, it's not considered this. The many designers that are not familiar with high frequency effects don't believe this coupling until they see how important it is. Every time you have inductors, including inductors with closed cores like toroids, are really good creators of magnetic field through leakage, or they can attract a magnetic field very easily. So it's impressive how you can destroy the efficiency of a filter or a system with this kind of location. Is the best option is to put the input and the output one close to the other. If you see to my camera, I will show you one idea related with this. Let me show you very quickly. This is one PCB. This is one PCB that is designed with the input voltage here and the output voltage here. So what happened? The output filter is here and the input filter is here. It's one close to the other. The difference in emissions is really impressive compared with this one. It's close to be the same. It's close to the same PCB. But one of the difference between them is that here the input voltage is here and the output voltage is here. Sorry.
Yeah.
Sorry.
Yes, I was going to interrupt you, but thank you.
Sorry. This is the same. You can see here the original board, where you can see here the input voltage and the output voltage. So that means that the input and the output are one close to the other. You have the filter. Between these filters, they have a strong coupling. The only possibility is to introduce in the middle some kind of shielding, no? Or some kind of orientation that minimize this coupling. This effect of coupling is increased if you use potting. If you use potting, the potting is usually a dielectric material of a constant between 3 and 6. So you will be increasing the capacitive coupling between the components in the input and the output. Another strategy is to do this. It's the same circuit, but what I am doing is to put the input voltage here and the output voltage here. So they are in separated areas. This can have problems in radiated emissions, because with the cables here and here, you can create easily a dipole. But considering all the risk and your system, where the connectors go, you can solve many problems. But you know that sometimes solving conducted emissions, you destroy radiated emissions.
Okay. Is there a big difference between semi-shielded and full shielded inductors to reduce noise at the output? Or is it better to have a smaller size in the inductor?
I prefer the small size inductor, but obviously a fully shielded inductor is better for EMI. Okay, but where you put the inductor and how is the orientation and how is the size is really important. And additionally, in another comment, I was saying in a previous comment, let me show you this screen. You will see that in many inductors, the manufacturers put a dot. That means that like the inductor has polarity, no? That is because if you look at the inductor, and this is the core, the dot explain where is the origin of the winding, okay? So here is the winding, several turns, and this is the starting point. So if you connect this to the starting point, let me show you here. This is the switching node, and this is the output. Consider, for example, that you are working with a DC-DC converter, no? So, sorry, this is a diode, something like a diode here, okay? So this is the switching node. You have the switching node here. The advantage of the dot point connected to the transistor switching node is that the internal part of the inductor is the node that is experimenting the DVDT. So this winding here, the external winding, is creating some kind of shielding because the external winding is connected to a constant voltage that is V out. You don't have DVDT. That is because it's additionally, if you are measuring with, for example, a Rogowski coil, if you are interested in the current in the inductor, it's better to put the Rogowski coil here. Here is the Rogowski coil. Here is the Rogowski coil. This is not good. This is good. Why? Because here you have a strong DVDT, and here the DVDT is 0. So Rogowski coils are very, very sensitive to DVDT. So these kind of things, small inductors and considering this kind of techniques from manufacturers are very, very useful.
Great. And then another, I think this is inductors as well. The end of the winding to the least noisy point. Not a lot of detail in that one.
Yeah, that is.
Can you point out the schematic, the capacitor which was added at the end to reduce the measured noise of the first circuit?
Okay, I suppose that he is saying this one.
It's near the end of the presentation.
But I suppose that he says about this, no? This capacitor, I suppose. It's referring, no? With this capacitor, I was able to reduce the noise a lot.
Yeah.
I am not sure if he's referring to this one. Anyway, let's try to go in this idea. And this is my filter. My filter is an X capacitor. It's a common mode choke. It's another X capacitor. And then I have two Y capacitors. One is here and the other is here. So these capacitors were connected with a wire. So if I don't connect these to ground, the Y capacitors are doing nothing. Okay. This is 4.7 nanofarad capacitors. I think is what he's asking.
Okay, great.
If not,
thank you.
Let me know. Okay.
Let's see. Is it better to use a ferrite bead instead of an inductor?
No, it's different. It's different. Remember that when you are, I don't know exactly where you refer to use a ferrite bead instead of one inductor. Obviously, in the output of the buck converter, it's impossible because you need to storage energy and you need one inductor, no? And if you are considering some kind of filtering, this is the same idea. Remember, with one inductor, you have, in theory, it's like you have ohms related with omega L. There is no dissipation. Obviously, you have a small resistance that is related with the copper or losses in the core or something like that. But the important thing is that you are interested in microhenries or in millihenries, something like that. But when you are working with a ferrite, the idea is that you are working with something, the impedance of this inductor is something like this until you arrive to the resonant frequency. But with a ferrite, the impedance is doing something like this. And what you are interested is in the area where the ferrite is resistive, not in the area where the ferrite is inductive. This effect is totally inductive, reactive, this inductive, no? So when we select a ferrite for EMI purposes, usually we are interested in selecting a frequency, the frequency where we have the problem, to introduce losses. So the EMI, let's say, disappear, is converted to heat. But when we are using inductors for filtering, the noise don't disappear. The noise is reflected to the source. Perhaps can do some problems or not. So it depends on the application.
Okay. And we have knocked off a lot of questions, Arturo, and our list is getting longer. We still have a list of 25, and we're going to have to cut this off at the top of the hour. So I apologize to everyone. we'll have a discussion with the panelists and see what we might be able to do to address all these questions. Great stuff that you've been going through. Let's try and knock out a couple more, but I think we are going to have to call it good at the top of the hour. What is the main reason to place the input filter on the opposite side of the power supply at the second board?
Yes, this is what I answered before, is that in this way, you minimize the coupling, the parasitic coupling between the DC-DC converter and the output filter. So the output filter is not detecting magnetic field, basically magnetic field coming from the DC-DC converter. It's some kind of shielding. You are using the inner layers to separate both areas.
Could the same method be used to separate differential and common noise using a donut?
I suppose, I don't know what is a donut, because donut for me is something very sweet, but I suppose that is referring to some kind of transformer to add or subtract the output of the two LISNs. If this is the equation, yes.
I see further down they clarified like a pribe current.
Yeah.
Yeah. Okay. Yes, we will send out a recording of all of this.
The donut is a probe current. Yes, you can do something, but not easy, because when you are measuring in a cable, differential mode and common mode, the measurements are very, very affected by the position of the current probe in the cable. So be careful about that. But you can do things with a current probe.
In the case of an AC-DC converter, when the heat sink needs to connect to somewhere to avoid the EMI, so where should it be connected?
Considering that the heatsink is working with power devices, the general answer to this question would be to the power ground. So the activity that you are injecting from the device to the heatsink is returned to the ground of the power system. But obviously, you can have some problems, for example, with safety, or for example, with immunity test. And then you need to apply other solutions, no? But the idea is to put the heatsinks at a constant voltage, so he's not floating, he's not experimenting DVDTs.
Should I put some elements or trace below the inductor or the transformer?
No, never. Below the transformer or the inductor, the best option is to put ground plane as close as possible. Yes, you can change the value of the inductance and you can introduce some losses, but in my experience, this is not a very big effect. And it's more important to contain the energy in the area of the inductor, not spreading the energy around the system. Remember that in AMI, answers must, the best answer is it depends, but let me say never.
Great. And sorry, but I think this is going to have to be the last question. Is it possible to characterize common mode and differential mode noise with a current probe?
Yes, you can do that. Is the same idea like previously, but the idea is if you have two wires, something like this, and you want to measure the common mode, you do this, so you will get common mode. And for the differential mode, you do this. Let me draw here. You take the current probe, you put in this area, and then the element goes in this direction. Yep. So the output of this current probe is 2 times dm. This is the correct way. But what I was explaining is that depending on where is the current probe located, is here or here or here, the measurements can change a lot because there is a transmission line and you have reflecting waves and you can have maximums, minimums, zeros. So you need to put the cables very, very fixed in position.
Okay, and I think we're going to have to call it good at that point. And thank you, Arturo. You stayed with us a half hour extra long and lots of great answers, but we really appreciate your input. For those of you whose questions we didn't get to, I apologize. Remember, we're going to be back next week, so maybe we can get to some of this then, but appreciate all the interaction and input that everyone was able to provide today.
Okay, thank you very much, and thank you for the invitation to MPS and Rodenswar to be here with all of you.
Thanks, everyone. Bye now.
Bye-bye.